So here we go. Here we go. So last time we were looking at, here's our header. Again, it's our nice squishy world. We don't need to deal with generics right now or templates or anything. So what do we have? We've got, okay, include rectangle. We need to do that because we're going to be making use of the rectangle in this class. And class square, but then we've got this colon public rectangle. That's the syntax. That's the code we write to tell C++, okay, I'm making a new class called square, but I want to inherit from rectangle. That's the magic code. And then what do we have? We've got our constructors, deconstructor, a toString, and getSide. And getSide was neat because getSide didn't exist in the rectangle class, so we're adding something to it. But toString did exist in the rectangle class, if you remember. So what we're doing here is a special thing, and we're going to talk about it more in a moment, but this is called overriding. We are saying, like, look, I know that toString exists in the rectangle class, but I'm going to have to define my own. I want a special toString that's going to be special for square. It'll differ from the rectangles. But I also get all the functions, methods that were in rectangle, which was like getLength, getArea, and whatnot. I get those for free, even though I don't have them written here. So because I wrote like toString, that kind of like indicates to me that I'm going to be overriding it. Oh, and we get the attributes for free as well. We inherit them. So what should the constructor look like? Well, we're just going to hijack the rectangle's constructor. Here's the default constructor. The default constructor for the rectangle set its length and width to 0. Okay. Is that really a rectangle? I don't know, but who cares? You're shaking your head, no? Okay. But what we're saying here is like, okay, if someone calls the default constructor for square, just automatically call the one for rectangle. Just kind of like pass it along, right? I have to write this, but it's kind of like passing the buck. Yeah?
Why is it out of the brackets?
Because that's the syntax, right? So I know what you're thinking. It's like, oh, why don't just call the constructor from within the function? That's not how we do it here. It's just, you do the colon rectangle saying like, yeah, just hijack that one. Here is the rectangles. So we just effectively call this. So, if someone calls the default constructor, okay, for the square, just set its length and width to 0 as well. How about this one? So let's look at the other constructor. This is where things get, oh, yeah.
Can you go back to that? Yeah. So you're saying in the main function, if you call the square from that one, then it goes immediately to the rectangle function from the other?
Yeah, it's kind of like the default square constructor is just like the middleman. It's like, oh, someone's calling me, what do you say, rectangle? It's passing it along. So here's the squares, because the squares constructor only took one attribute. But in this case, I guess I should hit next so you can see the rectangles. Look at what's going to happen. Take a second, look at this. Does this make sense to you? I don't even really need to explain to you what's going on. You should probably be experienced enough that you're looking at this. Even though you're like, well, this is new syntax, I think I kind of get it. What am I doing? Well, square, if someone calls the constructor for square that takes one double, what am I going to do? Well, I'm just going to hijack the rectangles, but I'm going to pass S, side length, for both attributes for the rectangle constructor, which would then be L and W. But of course, they're going to be the same value when I'm calling it because S is one value. It's kind of cool, right? Isn't that handy? It's like passing the buck. Okay, create a square of side length 1.2. Okay. Well, I'm lazy, so I'm just going to call the rectangles. But rectangle needs 2 attributes. Well, I'll just give it S twice. Length, width. LW. Isn't that neat? I think so. Copy constructor, nothing. We just pass it along, just like before. Deconstructor. It was declared as virtual in the base class, so we have to implement something here. But the fact that it was virtual isn't why I had to make it work. More on virtual later. It's a hairy thing that might not really matter to us so much in our nice cushy 162 world. So, get side, return width. Did I have to say return width? So I'm saying call return width. Return width is a function that I inherited, right? Which returns a rectangle's width. What would I change this to if I wanted? Return get length. Yeah, because it should be the same thing, absolutely. Right? Did I write the get width inside my square class? Did I write that inside the square class? No. I inherited it from the rectangle class. I got it for free. Where does it come from? The rectangle class. So the square has the length and width attributes. But funnily enough, we're not allowed to access them. How we declare them, because we set them as private, which means I can't even access those things, which is weird, because you almost feel as if you should. If I'm in C++, you think, if I'm inheriting from my parent class, shouldn't I have like direct access to even the private things, because it's kind of like the same class? Well, I guess we're actually in trouble here. We can't access those attributes directly. Because it's that would kind of break the rules about like, well, how you're supposed to interact with objects. We get the following for free: get length, get width, get area, and there was a toString. Those are inherited, and those were public. So we get toString method for free. Wait, I just want to make sure. Yeah. We get toString method for free, but that's the one for rectangle. We want a special one for square. Right? So if I called toString and I don't overwrite the one for square, and I call toString on a square object, what's it going to say? It's going to say rectangle length something width, same thing, right? That's what it's going to say. But I want one that's special for a square. One that's probably going to say that. Return square side is that. It's different. It's unique to the square. So now, if I tell a square object toString, it's going to look for the method. Is it written inside my square class? If it is, call it. If it's not, look at my parent class, right? Technically, you can have classes inheriting from classes, so you can keep looking up. But we're going to start with looking at like within my class. Yeah?
In that second toString in the return statement, you have get side. Can you have like get length as well?
I absolutely could have.
Okay.
I could have even written get width
Okay.
if I wanted.
Just because get side is just returning get length.
Exactly. Side, length, and width are all the same thing.
Okay.
Yeah. Cool. So this is called overriding. I got this method, this method, this method, and the toString method I inherited from rectangle from my parent class, but I'm saying I don't want that one. I know you gave it to me. Screw it. I want my own. And so we wrote it. Overriding. It's pretty cool. Any questions so far? Are we still okay? So if I said, okay, rectangle. I created pointer to a rectangle, create a new rectangle, 510. If I say r get length, what should be printed out? 5. Yeah, okay, I guess L was the first one. It was L and W were the two attributes. So length should be 5. Get area, what should that be? 50. toString, well, it should say rectangle, open bracket, length equals 5, comma, width equals 10, and so on. If I do a square, get length, can I call that?
Yes.
Good, I tried to, some people said no, but a lot of people are saying yes and nodding your head. Good, I tried to trick you. Because I get length for free, I got it. Get side, can I call that? Yeah, now, could I have called get side from R?
No.
Why not?
Because it is a side.
Bingo. Because a rectangle isn't a square, and the square's head gets side. Now, the square is a rectangle, and the rectangle's head get length, so it's fine. But not the other way. Yeah? Get area, can I call that one? Yeah. 36, I guess. toString. Which toString is it going to call? The one in rectangle or the one in square?
Square.
Square. Fantastic. You're catching on. Good job. So when we make something public, child classes can inherit from them directly, except for the constructors, but we can still access them by just kind of like calling them anyways. Cool? If they're private, child classes can't access these. That's the rule. That's the rule we have to follow. Why? Because that's the rule. But there's a new like visibility modifier called protected that we haven't used, but we could use. It can be accessed by any class in the same package, including the child class. Protected is kind of somewhere in between private and public. That doesn't mean go start making everything protected now. It's just FYI. We still can live in our world of private and public for the time being, but I'm just letting you know there's another one. You have a question?
Yeah, what is that same package?
Same package, so that's like, you know what, we haven't been talking about that. Let's not worry about it right now. Good question, but for all intents and purposes, for what we've seen so far in this class, it's basically the same thing as public. Inheritance, so why are we doing this? Well, it saves resources. And you might say, well, you could easily just copy and paste the code and change what you need. Well, that's true, but imagine you have like these giant pieces of code, like they're bajillions of lines long. And in what would be the parent class that you decided not to do inheritance, but you just made a copy for a child class, you have to change something here. Well, now you have to change them all here and maybe over here, depending on how many times you inherited from that class. It's a nice way to logically break up our stuff and kind of keep our data. It helps with like data and code integrity. So now we have to change it 2 places or however many places, whatever. If we don't actually have access, okay, what if we don't actually have access to the original code? So let me say, what if imagine there's a string class, okay, right? You didn't write that though, right? You didn't. But what if you want to create your own string class called like my superstring class, right? You want to do that. That's what your goal is. You don't have, you want it to do everything a string can do, but you want to add a little bit more because it's like special. Make sense?
Yes.
So yeah, I want to make my special version. So I want it to do everything a string can do, but do I have access to that string code? I don't. It's hidden away somewhere. I don't have that code. So I can't copy and paste it and make my own. But I can inherit from what already exists. I can inherit from the string class and then start writing my own stuff too. So it actually gives us a way to modify stuff that we might not even have access to. So here's the thing. The child class is a more specific version of the parent class. Like a square is a rectangle. But let me ask you this. Is a rectangle a square?
No.
No. It might be, but we definitely can't say that in general, right? Certain instances might be, but in general, absolutely not. So a square is a rectangle. So we can use is a, well, okay, we'll get there in a second. So given that a square is a rectangle, I can do this. Right? So this isn't crazy. Create a new square pointer as new square. But I can also do this. Are you happy with this? No? A square is a rectangle. So yeah, I can access it with a rectangle pointer because a square is a rectangle. So I can actually have a pointer of a parent class point to a child class. Isn't that neat? Pretty cool. Yeah.
Yeah, by having the pointer to the child class, doesn't that get rid of the ability to use the methods that are strictly?
Well, let's keep going and see where this takes us. I can also do this. Like I can create a new pointer, right? So before, like it's a new square. Before I was just pointing to something else, I can create a whole new one. And this is fun. So do you think I could make a square pointer point to a rectangle object? No. Right. Because of that whole is a thing, right? Like all squares are rectangles, so rectangles can point to them. But if I have a square pointer and it points to a rectangle, we might be in trouble. So this is basically what we had on the previous slide. Cool? Remember, S and R1, they're not squares or rectangles, they're pointers to those things. So in that box is the memory address, which again, we just like to draw as the arrows. So, the type of the object does not change. Everybody say this with me. The type of the object does not change. So does it change?
No.
Good. This is important because a lot of people start getting really excited about this and then start saying, oh, if I point to it with this type of pointer, can it pretend to be? No. The object itself, the square object, that stays the same. It's a square object, whatever, regardless of the type of pointer pointing to it. So what is the type of S?
Square.
Square.
Pointer.
So everybody say square pointer. Good. What's the type of R1?
Rectangle pointer.
Good. What is that thing?
Square.
Square object.
It's a square. It's important to remember this. I remember the first time I started learning it, I started thinking like, oh my gosh, I can definitely see how cool this is. And I was getting way too ahead of myself. Wasn't allowed to do that. The type of the thing, it's still going to be a square. So, okay, the type of the object does not change. It's defined when creating it. Square star S equals new square. Boom. This is a square. That's a square pointer. They're different things. R1, perfect. But R1 is still just a rectangle pointer. This object that R1 points to is still a square, right? So, polymorphism is the idea that behavior can vary depending on the type of the object. Yes?
Here we can write like rectangle pointer equal to new square of something, right? So in that case, what would be the
It's still going to be basically the thing on the right-hand side, which would be a square. So if I said R2 equals new square, still a square. Yeah. So it's like, see how it's like new square? The thing on the right-hand side, that's the object being created. It's of that type, square. Good question. So polymorphism is the idea that behavior can vary depending on the type of the object. So, I'm in this situation, which you were basically just asking. S is pointing to what? What's the type of the object S is pointing to?
Square.
What's the type of the object R1 is pointing to?
Square.
What is the type of the object R2 is pointing to?
Square.
Good. We're good. So far, so good. Now, if I say S to string, what do we think it's going to be? Squares. Right? If I say R1 to string, what's it going to be? Why? Because it's still a square. What about R2's to string? Same as before, what we just said. Yeah. Okay. So sometimes the computer won't know which method it's actually going to be running until runtime. Let's say I tell my code, here's a rectangle pointer. You're going to be pointing to a square or a rectangle. I don't know which. So at compile time, I don't know which version is going to be run. Let me show you an example of what I mean. It's a contrived example, but it gets the point across. I roll the dice. Imagine I've got this code, I haven't hit run. At runtime, at compile time, if I ask you which version of toString is going to be which version is going to be called, the squares or the rectangles?
Depends on.
Say it louder.
Depends on the random number which you are entering.
It depends on the random number. Effectively, it depends on what happens at runtime. So before I hit run, I have no way of knowing if I'm going to be calling the squares or the rectangles. When I hit run and I finally roll the dice, that's when I'll know. Isn't that interesting? So like this, yeah, pretty cool, huh? So if the method you're calling exists in the child class, then the child class versions get called. If the method you're calling does not exist in the subclass, then it calls the parent's class's version. That's it. So it looks at the child class. Do you have a toString? Yeah, okay. Run it. But let's say it calls the function getLength, right? It's going to look inside square and be like, okay, call getLength. But it's not really there. It's in the rectangle class. So it's going to call the stuff that was written in the rectangle class. Or if there was a parent to a rectangle that was like shape or something. Yeah. So you can only call methods that exist at the highest level in the hierarchy, though. Because here's the thing. What if I have R, which is like a pointer to a rectangle? R might be pointing to a square or a rectangle. I can't say, hey, R, get side. Because it doesn't exist in the parent class. Because if R happens to be pointing to a square at runtime, remember, this is like dynamic binding. This is like runtime stuff. At compile time, I don't know, maybe R, I have that rolling the dice thing again, right? I don't know. Like, if R is pointing to a square, we're fine. Right? Like, oh, we should be able to call it. But R could be pointing to a rectangle. And if R is pointing to a rectangle, and I tell that rectangle, hey, give me your side, the rectangle class is going to be like, I don't know what that is. What's get side? You didn't tell me about this. It existed in the child class, not the parent class. So this is bad. How can C++ know that R is going to be pointing to a square? As far as it's concerned, R could be pointing to a square or a rectangle. Basically what I just said. So if somehow we were absolutely certain that R was going to be pointing to a square object, if somehow we knew this, if we could guarantee it, right? We could do this. Remember how like I've got A and B, they're integers? And what is A divided by B? Say it louder.
0.
It's 0, not 0 point, no, it's 0. Why? Because it's an integer division. It needs to give you an integer result, so it just truncates everything. The answer is 0. But I could do this. Like, I could convert A to a double, and suddenly, like, it knows. So this is like casting. This is saying, like, okay, just pretend you're a double. So, yeah, like, pretend you're a double. So we can also kind of do this. So R gets side. What we could do, we could be like, okay, no, just pretend you're actually pointing to a square. Like, trust me, you're pointing to a square. Okay? It doesn't change the square. The square is going to be whatever. But just trust me. Trust me, you're going to be a square. Now, of course, you might be saying, how could you guarantee that? Well, more on that in just a second. So what do you think would happen if R really was pointing to a rectangle? We tried to say, oh, just trust me, you're square. We might run into big trouble because you're telling C++, oh, trust me, you're pointing to a square, but it's not. So C++ can get very angry at you. And it might have undefined behavior. So yeah. So type ID is an interesting thing I can do. I could say, here's a way I could guarantee. A moment ago I was just saying, we can cast. If somehow I knew that I was going to have a square, if somehow I knew that, but I still wanted to use an R, like a rectangle pointer, I could do something like this. I could check the types. I could check if something, like I could check the type of the variable and see, is the type, are they the same? Is the type, so look at the right-hand side, right? Let's say I've got some pointer that's pointing to a square. It's guaranteed to be pointing to a square. It's definitely a square object, okay? So pointer to square, of course I need to dereference it, because otherwise, I mean, the type of a square pointer is the type of a square pointer. But I want to make sure the thing that the square pointer is pointing to, I want to get its type ID. And then I've got this thing called pointer to maybe square. This is the suspect one. Are you a square or are you not a square? I don't know. If they're the same in this scenario, so I'm just checking if the type IDs are the same, well then cast it as a square and get this out, I'm good to go. If it's not, then just ignore it, do nothing. Because I can't do it, that's bad. So this is a way I can guarantee that I know the type, and then I can do the casting if I really want it. Cool, huh? Yeah. So everything could exist in some sort of hierarchy. We don't have to stop at just like 2 levels. Like I could have an animal, then have reptiles, birds, mammals, and so on, and so on, and so on. I can go on forever. Now in some programming languages, everything is going to fall into this hierarchy, whether you like it or not. So in like Java, for example, I'm just going to bring this up just so you're familiar with this idea. And Java is going to be very similar to Python too. In Java, if you don't inherit anything, if you don't say, oh, here's my new class and colon, I'm inheriting from this class. If you don't write that, that's fine. But Java shows up and automatically writes something in for you that says like inherit from the object class. In Java, we have this one omnipotent class that's at the top of the hierarchy, and it's the object class. Everything's an object. And then under the object, we have child classes and so on and so on and so on. So if you don't inherit from anything, you inherit from the object class to begin with. Okay, just by the way, a lot of times this doesn't really matter to you, let's say, whatever, who cares? You just get it for free. Now, let's say we're talking about Python now, because you're familiar with Python. You automatically inherit from this God class. You have to, even if you're not inheriting, you inherit from this one for free. If you're inheriting from another class, well then that's fine, because that class must have at least inherited from the object class, right? So if I'm not inheriting from object, but I'm inheriting from this one, well then object is in my lineage somewhere. Let me draw what I mean. Seeing some blank faces, so I want to make sure. Here's the object class. If let's say below it I have like the string. Let's just say I've got the string class. And then I want to come up and make a new class called the rectangle class. If this was Java or like Python, not C++, C++ isn't going to do this for you. You know, pros, cons. I'm just showing you an alternative. If this is Java, even if I don't write inherit from object, it's going to. No matter what, you get it. So if I show up and I say, no, I'm going to make a square class, but I'm going to write in that I'm inheriting from the rectangle class. Okay, but object is still in my lineage, right? So it's an interesting way to make sure that all things you write, all classes, are going to have the object class somewhere in its lineage. If you don't write anything, you get it for free. If you write something, you get from that thing. And that thing, there must be somewhere in its lineage the object class. Because, like, do you kind of see how it's kind of like recursive actually? How it's like, if you don't do it, that's kind of like the base case. If you don't do it, you get it for free. If you do it, then that one must inherit from the object class either directly through the base case, or it must be inheriting from something that must have inherited it for free. Do you kind of see? It's kind of cool to think about it recursively, but it's totally what's happening. Yeah?
Is this why in Python, if you make a class and you don't write a repr, and you try and print that object, it'll give you the memory address, because that's like the top class's like default thing to do?
You just said something that just made me the happiest person on earth. So let me ask this question. Knowing what you know about Python, and now knowing what you know about inheritance, what methods do you think you're inheriting? Like, what methods are written in that object class? Repr, just like you said. So in here you have repr, which means in here you have repr, whether you override it or not. If you override it, it calls this one. If you override this, it calls this one. If you didn't override, what's it going to do? It'll just print out the memory address. Well, that's what this one says to do. Oh, just print out the memory address. Is that useful? Eh. So in your more specific thing, you make a better version, and so on, and so on, and so on. You also get like an equality check for free. Now the equality check for free you get is it checks if like the 2 pointers are pointing to the same thing in the memory address, and same thing, right? It doesn't check like, if I have 2 James Hughes objects, it doesn't check, oh, are their attributes the same? It'll only be true if we have 2 pointers to the exact same thing. But I could make 2 instances of me, and it would be, are you equal? And it would say no. So I would have to like go and override it to make it appropriate for me. Point being, you asked an amazing question and you made me so happy. Because you get it. Did his point make sense? Yeah, I'm seeing a lot of nods. Good. It's good. If it makes sense, you get it. Cool. Any last questions about this? All right, cool. So we'll start with lists, but we probably won't get very far. Lists, I guess, currently aren't up on Moodle, but that's fine. I'll put them up after class. So, lists. Who remembers lists from Python? All right, you know lists. So the point of this lecture is, what's a list? Well, we already know that. What is an ordered list? I'm willing to bet you might be able to figure that one out. What's an unordered list? What's an indexed list? And we're going to look at an array implementation of a list, and we're going to discuss a list implementation of a list. But I guess maybe we won't actually get to the actual implementation today, or through this set of slides. So, like a stack and a queue, a list is just another linear data structure. It's something that's going to hold on to information. We can start somewhere and ask, okay, what comes after, what comes after, what comes after? It's the basic idea. But lists are going to be more general than stacks and queues. We can do more with them. So lists are not limited to where you can add and remove the elements. Well, actually, that's worded poorly. Really what I meant is stacks, the adding and removing always happen from one end. Queues, the adding always happened at one end and the removing always happened at the other end. Lists, you got more freedom. We can do more. A general list. So they're more general than stacks and queues. So lists, we'll start talking about what makes a list. So then we'll discuss 3 different specific ideas of a list. What I want to get across here is it's kind of like we're building on top of the idea that, so we had a stack before, right? That was the idea. But then we had 2 different implementations. Array and linked. Same idea with the queue. Now, what I want to do is kind of take this to another level for the idea of a list. I want to talk about, okay, I want to have a list. A list is a high-level idea. But you know what? I'm going to want 3 special types of lists. I'm going to want an ordered, I think I had unordered, and indexed. Okay? So I'm kind of like moving up another level from this. we had the idea of what we wanted to do, and then we had the implementation. Now what we want to do is we have the idea of what we want to do, then we have more specific ideas of what we want to do, and then we can have different implementations of each. So this isn't the implementation level. This is still like the idea level. It's still the like how level, not the wait. Like still the how I use it, not how it's implemented. But I've kind of like moved up a level. Any idea what might come up? Some topic we may have just learned about?
Inheritance.
Yeah. We've got lists. Do you think an ordered list is a list? Yeah, it kind of makes sense. But we'll get there. We'll get there. I jumped ahead a bit. So though there are literally a potential for an infinite number of variations, we're going to look at 3. Ordered lists, unordered lists, and index lists. Index lists, that's going to be what you're familiar with in Python. You've been using index lists for a long time. You love them, right? You can add things to the end. You can get things from wherever. You can insert. You can do whatever you want. Way more general than the stack and the queue. So here's the general idea of a list. We have the front, and we have a rear. Cool. What things might you want to do to this list? Add things? Sounds good to me. What else? Remove things? Seems reasonable. What else might you want to do? Get the size. Are you reading my mind? What else?
Empty.
If it's empty, oh my gosh. Good for you. Wow, that's impressive. Yeah, that's the general idea. Here's a very high level list. We're going to want to be able to add things to this data structure, remove things, see how big it is, and check if it's empty. Right? That's the highest level stuff. Now you might say, like, well, how are we going to add? Well, I mean, that depends on a couple of things. Hang in there. So add things, how do we add things? Where do we add them? Remove things. How do we remove them? Where do we move them from? Size, well, that one's actually pretty easy. Kind of doesn't really matter what type of list it is. The size is, well, how many things are in there. And is empty the same idea. But what else might we want to do? So adding and removing, the how and where matters. The adding and removing is the very high level idea. We definitely are going to want to add things and remove things. But how? Because if we have an ordered list, there might be special rules. Unordered lists, whatever. Index lists, whatever. Like, there might be special rules depending on the type of list. When we add things, when we remove things. So the idea is we want to add and remove. But how? It depends. And then when it comes to the implementation, well, I mean, sky's the limit. Do whatever you want. As long as it works the way it's supposed to. Any questions? Do you have your hand kind of up?
Oh, it's just, I think you asked what else you might want to do.
Yeah, what else might you want to do?
Implement some kind of list comprehension kind of thing where you could add one list to another list, put it together, and then somehow do like, I don't know, implement some kind of divide and conquer to be able to order them.
Yeah, so maybe, I like that idea. Maybe what we might want to be able to do is what happens if you try to add 2 lists together? Like a concatenate idea.
Yeah.
Maybe we want to be able to concatenate 2 lists. So I can write a function called concatenate that takes another list and then it returns this one plus that one. Yeah, that's actually very reasonable. We might want to do that. We might want to get a reference to check if there's, well, I guess that's the is empty. We might want to get a reference to the front, maybe kind of like a peek idea, or first, remember that? Like peek and first. Like don't remove it, but just have a look. From the end as well. Yeah. I mean, I suppose we might want to be able to do that anywhere, but whatever, I don't know. So we can do whatever we want, really. So when talking about adding to a list, the question is where? That depends. An ordered list, for example, is a list where all the elements in the list are ordered. Now, the ordering will depend on some characteristics of the type of the things in the list. If I gave you integers and said this is an ordered list, you kind of can figure out the ordering. Like, okay, it's ascending order probably. What What comes after 2? 3. Good. But if I say, let's say I say, okay, here's this marker, okay? And here's this marker. Which comes first? What comes first? I mean, it's a simple question. What's the problem?
There's no order to it.
I mean, what's the ordering? Like, I mean, that's a silly question to ask, right? If I say, oh, what comes first, this laptop or that laptop? That one, why? Because it's better. Okay, so now you've now applied some ordering to it. Because this one's better than that one, apparently.
I have no idea.
You have no idea, yeah. But the point is, some things have an intrinsic ordering, some things don't. And that's fine, because we can actually define objects to have like an ordering. We can say like, oh, how you compare to each other. So some ideas have an ordering, like integers. They have an ordering. We learned that when we were this big. Markers, there, I guess we can order them on height. Length of the marker. Perhaps that's a reasonable ordering. Maybe I order them based on wavelength of the color. Yeah, okay, why not? Or maybe I order them based on how much I like the color. Like based on my ordering of my favorite colors. Or maybe I order them based on how much marker is left. Or how much time it's been used. How many people have used it. I mean, whatever I want, I get to define it. Remember, we're in the world where we're defining the stuff now. So, there we go. So, ordered list, if it's integers, okay, not bad. But the elements themselves determine the ordering. The elements have the ordering. The list doesn't. The list will help me, like, keep track of that for us.